Hi, everybody. Today I am calling the lesson The Lab because I'd like to do some work um, on your hypotheses and your procedures that you turned in last week. Just fine tuning those and making those the best that they can be before we do our actual experiment tomorrow. So remember that the premise of this lab, this ecological tolerance lab, is based on material that we've learned about in the past couple of chapters in your textbook, right? We've been kind of figuring out that certain species, certain organisms, they have this range in which they can live. And we have certain areas of that range in which they can really be successful, reproduce, grow, and kind of thrive. And then on the outer edges of those ranges, they don't do so well. They maybe can survive, but not well enough to reproduce. Or sometimes, if they get too far out in the extremes, they can't survive at all. So, in this lab, we're going to kind of explore this concept of ecological tolerance by testing how yeast responds to different environmental conditions. And specifically, temperature is what we're interested in this case. So remember that yeast, it's a living organism, and when it is put in a solution with water and some sugar as fuel, it kind of eats that sugar, if you will, and creates energy out of it. And in that process of creating energy, the yeast releases carbon dioxide and it creates bubbles in that solution. It carries out something called cellular respiration. That's what causes those carbon dioxide bubbles to form in the solution. So, just like many other species, yeast has a range of temperature in which it performs the best. And so the idea here is that we test different solutions of yeast and different temperatures of water to determine the optimal conditions for yeast to thrive and conditions where maybe it won't thrive at all. So this experiment really helps us determine how an abiotic or a non-living factor like temperature, right? Temperature is not alive. It's not a biotic factor. It's an abiotic factor. It shows us how that abiotic factor of temperature can have an impact on biological processes in an organism. And that's a key idea in ecology and in environmental science as well. So we're starting with the hypothesis. So remember, you learned all of this last week, that the basic formula for writing a scientific hypothesis is the if, then, because formula. So you take if the independent variable changes in some way, like if we increase or decrease the independent variable, then it will affect the dependent variable in some type of way because of a scientific law or some type of fact that we know about science and how it operates. So the example that they give you here, Alice and Adam are testing to see if giving the teacher compliments reduce the amount of homework given to the class. Identifying the independent variable, that's the compliments, right? The number of compliments. And then the dependent variable is the amount of homework given to the class. So we're trying to see if increasing or decreasing the number of compliments also increases or decreases the amount of homework that the teacher gives to the class. So what's the because here? Well, the because that they came up with is because the teacher will be in a better mood. And we know that logically, if you're in a better mood, you're probably going to assign maybe less homework, right? So the hypothesis that Alice and Adam come up with, their assumption or their guess here is that if the number of compliments given to the teacher increased, then the amount of homework will decrease because the teacher will be in a better mood. So more compliments causes less homework. So this is the key factor here. You can't just list the independent variable and the dependent variable. You have to tell me whether you think that the increase or decrease of the independent will cause an increase or decrease of the dependent. There has to be some kind of change that you're predicting here. So, in terms of our experiment, I asked you to identify the variables that are found. And these are some of the answers that I got. You guys mentioned that as far as the independent variable goes, the temperatures, the varying temperatures, you all identified that that was the independent variable. And you were correct on that. We're going to use temperatures as the independent variable here because that's what we're changing. We're going to have some high temperatures, we're going to have some low temperatures, we're going to have some temperatures in the middle. We're going to see how kind of that impacts things. So as far as the dependent variable, the one that I like the best is how yeast expands and performs. I got a couple of other answers here that you guys gave that you can read on the screen, but I think this is a good one. But I think we can do even a little bit better than this answer, and that is actually the dependent variable is the amount of carbon dioxide that's released by the yeast. How yeast expands and performs, that's true, we are looking at that, but how are we going to measure that? Well, we measure it through the amount of carbon dioxide that the yeast is releasing. And so I think this is a more specific and accurate dependent variable that we can test realistically in our experiment. So we've identified the independent variable, that's the temperatures, and we've identified the dependent variable, which is the amount of carbon dioxide released by the yeast. Now, the control variables that you guys gave me are the following: the yeast condition, how much there is, the ranges of temperature, the temperature and the sugar levels, the temperature and yeast amounts. And yeah, I think all of those work as controlled variables, right? We do need to keep the temperatures consistent. You all need to test at the same temperatures if possible. The condition of the yeast, whether it's new yeast or really old yeast, we do need to make that consistent in our experiment. How much yeast we use, how much sugar, all of those things are really important in controlling our experiment to try to get the most accurate data that we can. So you guys are definitely on the right track with those answers there. All right, so a reminder here. With the hypothesis, you have to use the if, then, because structure in your hypothesis. So let's look at the answers that you guys gave. Here's one that I got. The higher the temperature, the less it expands. So something to point out about this one, you gave me an independent variable here, and you also told me how it would change. And I like that because you said a high temperature or a low temperature. So it's giving me some more specificity here. The second part of it, the less it expands, for it, you need to tell me what it is. I'm assuming it is the yeast. So you want to list that out for sure. And then also there's no because here, right? Why would increasing the temperature cause the yeast to expand less? Or I'm assuming what you mean is give off less carbon dioxide. Why would that happen? So needing the if, then, because here. Another answer that you guys gave was the warmer the temperature, the better the yeast will perform. Again, the first half of this, on the right track here. Warm temperature or high temperature, they kind of mean the same thing. So I like that. The better the yeast will perform. What do you mean by better? Do you mean it's giving off more carbon dioxide? I'm assuming that's what you mean, but you have to kind of state that so that I don't have to assume what you might mean by that. And then again, if, then, because. We need that structure in the hypothesis. And then the last answer I got was if the temperature is too cold or too hot, then it could affect how the yeast performs because it will either be too much or too little. I like that we have if, then, because in this hypothesis. That's a good basis here. The problem with this hypothesis is that it doesn't actually tell me your guess, right? It's just saying if the temperature is too cold or too hot, it could affect how the yeast performs, right? We're not getting a clear guess. Your hypothesis has to give me a clear guess of what you think is going to happen. So staying in this kind of middle of the road, I'm not really sure if it's too hot or if it's too cold, that could do this or that could do that. I want you to stick to one side. So being confident, it's okay if your hypothesis is wrong. That's okay. But we need to have something to test against. So we need to have a clear hypothesis with a clear guess. So another way that you could spin this hypothesis here, this third one that we're talking about, you could say, like, if the temperature is too extreme, either too cold or far too hot, then it could negatively impact the performance of the yeast or negatively impact the carbon dioxide release of the yeast. So what that's saying is, if the temperature is on either one of those ranges, way too hot or way too cold, that the yeast will not thrive. So that's another avenue that you can go. It's still clear, right? I hope you guys hear that it's still a clear guess, even though you're not pinpointing hot or cold, but you're saying extreme temperatures negatively impact the yeast. So that's definitely something else that you could say. And the final point that I want to make about this is the because section. Because it will either be too much or too little. Well, too much or too little of what? Temperature, energy, what are we talking about here? So what comes after that because has to be a scientific reason that supports your hypothesis. And so to help you with that idea of the because, I want you to think about that ecological tolerance kind of bell curve that we looked at in one of your chapter sections that talks about how when environmental conditions are too extreme on either end, then an organism cannot survive. It must be in its prime kind of range of the ecological tolerance curve to be able to thrive. And so that's the idea that should be in all of your because statements, is that conditions have to be optimal for an organism to thrive. And if they are not optimal, then the organism cannot thrive. So for our hypothesis revised, to kind of help you guys out, we need to have the if, then, because structure. So I put this slide on here so that you can pause, copy it down if you need to, but this is the structure that we are going to use. So filling in the variables that we found, right? If the independent variable of temperature changes in some way, then the dependent variable of the amount of carbon dioxide that's being released by the yeast will change in a certain way because of some sort of scientific reason that we talked about. So we fill that in. If the temperature increases or decreases, then the amount of carbon dioxide released by the yeast will increase or decrease because yeast can carry out cellular respiration more effectively in warmer or cooler temperatures. This is a sample that you can use to help you revise your hypothesis. You do not have to copy this exactly, but I want to give you a lot of support if you feel like you're struggling and you really don't know where to go. Use this bottom section that I gave you, and then you just decide whether you think increasing or decreasing will affect the carbon dioxide in a greater or lesser way. That's what you need to do here if you really need support. If you feel confident that you have some other ideas and you want to expand upon this, you're welcome to take this a different direction. But you need to use the if, then, because structure in your hypothesis. So what I want you to do now is to take out your science notebook and write down a new hypothesis based on the feedback that I gave you, based on the structures that we talked about. So pause the video now, think for a few minutes, and come up with your hypothesis that you're going to use for tomorrow's experiment using the if, then, because structure. Again, you can copy what I've given you here, or you can take it your own direction. So pause the video now and work on that. All right, now we're going to talk about the experimental procedure. So in this section of your lab report, the procedure is detailing what you did in the order that you did it so that another scientist could repeat the experiment and get the same results, right? That's the only way that we can validate the work that scientists do is by repeating the experiments that they do over and over and over again and making sure that the results are still consistent. And that's so critical. That's why the procedure has to be written in a way that is repeatable. And that's why it has such specific kind of structure and qualities about it, is because it's so very important in the validity of science. So here's a sample procedure. You've already read it before because it was in one of those sample papers that I gave you, sample lab reports that I gave you to read last week. So I want you to read this sample procedure. You can pause the video, read it, and then we're going to talk about some good qualities. All right. So the first thing that this procedure does really well, and by the way, this procedure is not perfect, but it's a great starting point and it's a great goal for you guys to get to with your procedures as well. It's got a really nice, clear experimental setup. So the procedure clearly describes how the experiment stations were set up. Specific lab equipment is listed, right? Bunsen burner, burner ring, burner pad. You know exactly what the scientists use. This really helps to ensure that another scientist could replicate this experiment, and that's, right, a core goal of good science. Another thing that this procedure does really well is the scientific language and the kind of tone that it has, right? It's very formal, it's objective, there's no kind of emotional language here, there's no slang, there's no we dumped the stuff in the stuff. Everything's specific and formal, and that is incredibly important in your procedure. Specific and formal scientific language. If you don't know the scientific term for something that you want to put in your procedure, Google it. I mean, use the resources that you have to help you get to this tone, this structure, and this formality. In addition, this procedure is written in past tense. And this is how you need to write your procedures as well when you're reporting lab work in past tense, like you did it in the past. Even though you guys are writing your procedure for an experiment that you haven't done yet, right? You're not going to do it until tomorrow. You need to write it as if you did it last week, right? You need to write it in the past tense. The team set up. We only had, we inserted, we were, we decided, we prepared, we added. All members of the team were. We then heated, we recorded, we repeated. All of these verbs are in past tense, and you must write it that way. It can be tempting to write in the imperative, like mix the solution, heat the solution. But that's not how you want to write your procedure. You need to write it in the past tense. Now, in a higher level procedure, we would want to remove these pronouns. We don't really want to say we. You don't want to say we or I or you, typically. But overall, this is a really good procedure. And I'm willing to overlook those things because it does a solid job at what it needs to do, which is help you replicate the experiment. And it's written in the correct tense. And so that's very important as well. All right, let's take a look at your procedures that you wrote. So the first one says, first get the yeast and water and make sure the yeast and water are mixed, and then try to cook the yeast at different temperatures to gather data. So things that this procedure does well, it recognizes the independent variable by referencing using different temperatures. And that really shows an understanding that temperature is the variable that's being tested here, and that's important. It also indicates experimental intent. So this student understands that they're performing an experiment to test yeast reactions with different temperatures, and that's also a plus. And it shows kind of an early attempt at sequencing, right? We have the word first, and then we have the word then, and that shows that there's some sort of order happening here. But this procedure is really too vague, and it's not complete. There's not enough detail to repeat the experiment. If you were to read this and then try to repeat exactly what this scientist did in their experiment, you would not be able to replicate that. It doesn't explain specific steps, amounts, or actions, so it's really hard to repeat. There's no measurable quantities or defined variables. Like this procedure doesn't say how much yeast or water to use, what temperatures to heat the water, or how the results will be measured. So that's kind of a big con here. Another thing, this one uses really informal, like recipe style language. So phrases like try to cook the yeast in those directions with the imperative mood, you got to replace that with more formal language. And right, we want to do everything in past tense with our scientific papers. Okay, this procedure, we changed the temp to a lower temp to see how the yeast would react. So again, this does identify kind of the general experiment that we're doing, and that changing temperature is part of testing the tolerance of the yeast. It does show experimental purpose, which is good. We're doing it to see how the yeast would react. Yes, we are doing that. And it's got the right variable focus. It pulls out temperature, it pulls out the reaction of the yeast, and that aligns with the ecological tolerance concept that we're going for. However, right, still really incomplete and definitely way too short. Compared to our sample procedure, this procedure is like one sentence. And so it's far too simple for what we need to do. There's also no comparison or control conditions. It only mentions like lowering the temperature, but in a good experiment, right, we want to see what low temperatures and high temperatures would do to the yeast and the condition of the yeast. And there's also no mention of any measurement methods, right? How are we going to measure the carbon dioxide? We don't know in this procedure. Then finally, we have first grab your yeast and water. Put the water on the yeast, making sure the yeast is fully wet. Once you have done that, let the yeast sit for about 2 to 5 minutes and then start to mess with the temperature. Record your temps you use and how the yeast reacts. So this one shows an awareness of how we activate the yeast. We do need the yeast to sit in water before being tested. That is absolutely true. This one also includes timing, which is great. We have 2 to 5 minutes. That's a big range, but it is at least some time that we have here in this procedure. And then it recognizes that we need to observe and record the data. And this is crucial because you do have to document the results. Of course you do. This one, it still has some kind of unclear and non-scientific phrasing. Mess with the temperature. What does that mean? What does that mean you're doing with the temperature? That's kind of informal and a little too vague, so we need to know exactly what you plan to do with the temperature. There's also no clear method for temperature control, right? We don't know how the temperature will be changed or how it's kept consistent. Do you plan to put ice in the water to cool it down and then remove the ice? How do you plan to heat the water? Things like that need to be included in your procedure. And the range is a little bit too loose. 2 to 5 minutes, that's too big of a range. You need to have a specific number. Let the yeast sit for 2 minutes or let the yeast sit for 5 minutes. That way, a scientist could reproduce that exactly. Precise timing is really critical for scientific validity. So overall, areas to improve are clarity and detail, right? We need to add step-by-step detail so that someone else could repeat the experiment. Right now, our steps are way too vague. So we need to specify the exact materials we're going to use, exact amounts, the order of the steps, the timing, and how temperature is changed or held constant. The goal here is that the procedure needs to be detailed enough that another student could follow it without asking you any questions, that they could just repeat the experiment exactly how you've done it. Then we need to focus on our scientific language and tone. All of these procedures use like casual or conversational tone instead of formal scientific wording. Keep in mind, you need to use past tense like you've already done the experiment. Every word should be precise, no slang like mess with or stuff. Incorporate scientific vocabulary into your procedure. And finally, the measurability and variables. So you guys are thinking about temperature, but you're not yet kind of expressing those variables scientifically. So you need to clearly identify what you're changing, what your independent variable is. You're changing the temperature. And you need to clearly identify what your dependent variable is, that it's the yeast reaction. It's the release of the carbon dioxide. That's what you're measuring to see how that's impacted by the change in temperature. And then you guys kind of forgot to include your control variables in your procedure, that you're keeping consistent the amount of yeast that you're going to use, the water amount that you're going to use, the sugar amount, the time that you're going to let the reaction happen for, the containers that you're going to use for each one of these solutions. These are all things that need to be controlled or kept consistent for each trial. And so you need to specifically tell us what you're using so that we could also repeat it exactly. And you need to say how the results are going to be measured. Are you going to count bubbles? Are you going to measure it with like a ruler, measure the height of the bubbles? Are you going to measure the gas volume? What are you going to do? How are you going to figure that out? At the beginning of every procedure is also the materials list. So since you're going to be writing a procedure for tomorrow's ecological tolerance lab, I am going to give you the materials list that I think would be appropriate for the lab based on our hypothesis. So feel free to use this list to help you as you rewrite your procedure, and kind of stick to this list as closely as possible, because these are the materials that I'm going to have available for you tomorrow for your lab. So you're welcome to pause this and copy the materials list down. So what you're going to do now is you're going to rewrite your procedure. So after you write this draft of your procedure, I want you to do the levels check and make sure that your procedure is at a level 5. So you're going to write it, and then you're going to go to level 1 and make sure that you don't include pronouns. And then you're going to check level 2, and you're going to edit it to keep the sentences short but precise. Then you're going to go to level 3, and you're going to add specific values for the amounts of water, the number of trials, the time, temperature, all of that. Make sure all of that's in there. Then you're going to go to level 4. You're going to make sure that you have scientific terminology in here and how you're handling the controlled variables. These little details really show that you understand the role of controlled variables. And then you're going to take it to level 5. You're going to check out your procedure and make sure that it's in past tense and not imperative. You do not want it to read like it is a recipe. You want it to read like you're telling someone how you did this experiment. That is the goal. Make sure it's level 5. Because I want you guys to be able to use the procedures that you write today to guide you on how to do the lab tomorrow. It should be that good that you could follow it to do the lab tomorrow if necessary. That's the goal. So where we are now, here, here, and here, we really couldn't make a successful experiment from that at all. You want to get to level 5. That's where you want to get. Something that looks like this. That's the goal. So take the rest of class time, rewrite your procedure. At the end of class today, I want you to send me your new hypothesis with the if, then, because structure, and I want you to send me your new procedure of how you're going to do this experiment.